This will be our third and final video on Lenz's Law, looking at a few more examples of how Lenz's Law works, opposing changes in current. And something that we'd like to look at in this case right here is a pair of solenoids like this. And so I'm just drawing these boxes here for a bit of structure for myself here so we know what to draw. But the solenoids will look like this. We'll come up with some of those nice integral signs to make sure the wire wraps are very neat and visible so we know exactly what we're talking about. And this last one here will go down around the back here and come out like this. And what we have down here is we have a battery like this and a switch, and it goes up like that. There you go. So there's a solenoid like that, and we have a solenoid just like it right next to it here. Again, here's those wraps on there. It's going to come back around the back like this, and this last one here will grab it. And there'll be a resistor down here or a meter or some circuit element, doesn't matter what it is. So the question is when this switch gets closed, what will the direction be in that resistor right there? That's sort of the question in front of us. Okay, so let's just visualize one at a time. So what we'll do first of all here is just get the switch closed, like this. Close up the switch. So what will happen when the switch closes is that a current will flow, because this is a battery here, from the positive terminal around through the negative terminal. So the current's going to go up like this direction here. This is the current from the battery here. It's going to go up. It's going to go up around that back wire, and by the time it comes down around the front, there'll be a current flow in this wire, which is going to be down like that, and it'll go back around, it'll be down like this. The current's going to be down in all those coils, at least in their front faces there. There'll be a downwards current. So these green arrows are the downwards current in those black wires there. So if there's a downwards current like that, what magnetic fields produce? Well, if I put my thumb in the direction of the current down like that, and wrap my fingertips into the direction of that solenoid in like that, the magnetic field is going to point towards the right. So it'll fill this volume towards the right here with a magnetic field which points this way, but of course it doesn't abruptly stop there. It also just totally immerse the volume of this other solenoid over here with a rightwards magnetic field. So my marker is kind of dying here. It's supposed to be nice and orange, but it looks like it's sort of running out of ink. But here are those magnetic field lines, again, pointing to the right. And just to keep the drawing sort of the perspective there a bit, remember that these magnetic field lines always appear in the sort of the interior volume of that solenoid, interior volume right there. Okay, so the question is, Lenz's law is going to kick in. Here's a solenoid sitting here with this B field, which suddenly increases towards the right. What is Lenz's law going to want to do? It's going to want to counter this change here, and the way you counter a magnetic field which is growing to the right is you induce a magnetic field to the left to vectorially subtract out these orange magnetic field lines which are increasing to the left. So a magnetic field is going to be induced inside the solenoid to the left. So the question is, what direction in these wires what would the direction need to be in order to produce this purple magnetic field to the left? Well, I'll just take a guess here. I'll just take this segment of wire and put my thumb in the direction of current, wrap my fingertips around into the volume of the solenoid and say, well, the magnetic field is going to be over to the left like that. And that's exactly what I need them to be. So an upwards current over to the left. So the answer to this question is that there would be an induced current which is up like this. So my induced current is going to be up like this in this wire. And it's up in this one, it'll be up in this one, it'll be up in this one, up in this one, up in this one like that. So the B induced is going to be up. And if it's up here and sort of comes out like that, it looks like it'll be traveling that way in that resistor, which is the original question. So when you close the switch, the current in the switch in the solenoid with the battery, that current's going to be sort of downwards in these front-facing wires here. That's what we discussed just as the video got started here, although my drawing has gotten quite messy since then. Downwards current, that's a rightward magnetic field. As the magnetic field increases upon that switch closer in the region of this other solenoid over here, it's going to see this magnetic field increasing to the right. It would like to counter that by producing a magnetic field to the left. In order to produce a leftwards magnetic field, which is the induced magnetic field in the volume of the solenoid, I would need an upward pointing current in these wires here, which means the current must be going leftwards in this resistor to go up here and feed these wires in the upward sense. So that's sort of the answer to that question. And of course, because we can't leave enough alone here, what happens in the same system if the switch is abruptly opened again? Well, if the switch gets opened again, nothing changes about the direction of the current over here. It's just going to start getting smaller because the switch is open now. So if this current starts getting smaller, these orange magnetic field lines are going to start getting smaller. And I know that because the magnetic field of a solenoid is mu naught N over L times I. So B is proportional to I. So if I starts getting smaller, B starts getting smaller. So open the switch, these orange magnetic field lines are going to start getting smaller. In this solenoid over here, Lenz's law is going to see, look, these orange lines are getting smaller. We'd really like to build them back up again. So inside the volume of the solenoid here, we'd like to induce a magnetic field which is going to build up towards the right. So I need to sort of get rid of these arrows in here. Maybe I'll do it in a different color here. We'd really like to induce a magnetic field which is to the right like this. So in here, build up to the right like that. And to build up a magnetic field to the right, what direction of the current would we need in this coil here? Well, I'll just sort of guess here a little bit. I'll put my thumb in the direction of the downwards wire right here, and I'll wrap around. My fingertips will be in the direction of the volume of the solenoid that way. So I think that the induced current then would be this way in order to cause that to happen. Because if I put my thumb up in the direction of the way the induced current was in part A of the problem, and I wrap around the volume of the solenoid, I'll get a magnetic field to the left, but that's not what we need. We need one to the right to build up these decreasing orange magnetic field lines as they have originated from the solenoid over here. So the induced current is going to be towards the right when that switch gets open. And of course, when the switch has been closed for a long time, the current in the solenoid will stabilize. So if the current stabilizes, the magnetic field will stabilize. And if these orange magnetic field lines aren't changing anymore, there'll be no change in this solenoid over here, so the induced current will just drop to zero. So see, one problem can really give you three different answers to work on here: when the switch is abruptly closed, when it's been closed for a long time, and when it's been abruptly opened again. So let's look at one more example of Lenz's law here, and it looks like this. The circuit again. Let's say there's a light bulb here, and a light bulb here, and it's connected in a circle like this, or a circuit. It can be a circle if you want. And in the interior of this region here, there's a region like this that has a magnetic field that's sort of pointing in like this. So there's the B field. So there's two questions here. One is, what is the direction of the induced EMF what is the direction of the current in a couple of situations, and what will the relative brightness of the light bulbs be here? Okay. So A here, let's just say that B is increasing. So if the magnetic field is increasing as drawn here, it means that these arrows are pointing into the plane of the whiteboard and they're getting larger. That's what B is increasing means. So Lenz's law is going to kick in inside this loop here and say, even though this magnetic field doesn't fill the whole region here, it only fills the central region here, this loop here that contains the light bulbs is still witnessing a changing magnetic field. And again, it may not fill its whole volume, but it fills at least, may not fill its whole area, but it fills some part of it, and that's enough to trigger Lenz's law. So if B is increasing, you have to imagine these arrows pointing into the whiteboard that are getting larger. And what Lenz's law will do is go, okay, we need to start inducing a current in this loop to oppose that change. So we'd really like an induced magnetic field which is up like this. That allows to impose the increasing magnetic field down. So if the magnetic field is going to be up like that, this will be the induced magnetic field like this. Then what direction will it have to be in here? Well, if I put my thumb in the direction of this wire right here and point into the page, that's not the right direction because that's down as well. But if I come back this way, my thumb in the direction of current this way, wrap under this wire here, I can see that the magnetic field lines aren't coming up. See, my fingertips are pointing straight up. That's the direction that I would need there. So I need a current this way. That would need to be the direction of the induced current in order to cause that, oppose the increasing magnetic field into the board like that. So let's just say I then would have to be counterclockwise. Okay. Now in B, it might say something like the magnetic field is decreasing. Is decreasing like that. So what we have in a case like this here, let me maybe get rid of these induced B field lines here. Getting ink all over my fingertips, not too bad. Okay. So the magnetic field is decreasing, means these arrows are pointing into the whiteboard, but they're getting smaller in length. They're decreasing. So Lenz's law is going to kick in and say, well, we'd really like to keep those magnetic field lines from decreasing. Let's induce a magnetic field into the plane of the whiteboard like that. And how would we get that magnetic field? Well, if we put our thumb in the direction of current here and point downwards into the plane like that, that means we will produce an induced magnetic field which is into the plane as well. That would mean the current is going to be this way. So I then is going to be clockwise. That would be the direction of the current if that black magnetic field is decreasing as drawn. Okay, so remember the magnetic field we're talking about are these X's like that here. B is increasing and decreasing. So that's sort of the way that would go. And in part C here, of course, if B is constant, suppose B isn't changing at all. When that happens, you'll see the magnetic field lines still pointing away from you like that, but they're neither decreasing or increasing in length. They're just sitting there constant like that. And if that happens, there's no change in magnetic field. Lenz's law has nothing to do, so the induced current then will just be zero. There won't be any induced current. Now, as far as the brightness of the light bulbs goes, if you look at these light bulbs right here, the current that goes into one light bulb and makes it so start glowing light bulbs are sort of indicators of current like that. So here's sort of the glowing coming out of the light bulb right here. This is some current that's causing that to happen. Okay, so when that happens there, these light bulbs, turns out, are in series, because as the current comes out, it has to turn the corner, no choices, all the way down here, turn the corner, no choices, through this light bulb, and it's going to make this light bulb glow as well. But the point is that the current in this light bulb is the same as over here, because the light bulbs are in series. So if you have the same current, you'll always have the same brightness. That's just the way light bulbs work. For a given amount of current, they'll produce a certain amount of brightness, and that's the way it'll go. So at any time in this problem here, whether the current is clockwise or counterclockwise, or the current is increasing or decreasing, these two series light bulbs will always have the same brightness. So it's important to remember that. And there's even another class of these problems here you might find where there might even be a second light bulb in here that's going to look like this. So you might have the exact same system. I have 3 light bulbs in it. And just remember that these are all in series here. So the current that goes into one light bulb that comes out will be the current that goes into another like that. So all these light bulbs will always glow with the same brightness when they're in series like that. And of course the currents are coming from induced currents that went all the way back to a changing magnetic field in the interior region of the square. And what's the square circuit? And what's a little unique about this problem is that, again, the changing magnetic field region doesn't immerse the entire square like that. Like there's some other problems that maybe you've seen where the magnetic field was like this, and the loop in question was just a fraction of that. Like maybe the loop was like this. In other words, the loop was totally immersed in that changing magnetic field. It doesn't have to work that way. So of course, the area without the magnetic field does not contribute to producing induced current, but the area does not have to be filled with that changing magnetic field in order for Lenz's law to kick in.